Thanks everybody for coming. So this is the first of the summer intern presentations. There's going to be 3 today and 2 tomorrow, starting at 2:30. So this is the work that the interns have been doing for the last 2 months here in Dias for their internship. And so the first project is Matthew, Tim and Jack. They were doing their project under Denjo's supervision, and it's about Hamiltonian Monte Carlo simulations of the BFSS matrix model.
Love it. Okay. Thanks, Luke. Yeah, so that's our project. I'm Jack Murphy, this is Tim Daly, and Matthew is joining us from Switzerland. So we'll get started. Yeah, first of all, we'd like to just thank Dice for the opportunity. The last 8 weeks have been great for learning and for getting a bit of experience in the research field as well. In particular, we'd like to thank our supervisor, Denjo O'Connor, and as well we'd like to thank Shane Dooley and Yasmin Yazdi for coordinating the programme. So the outline of our project is I'm going to give you some background and I'm going to explain the Hamiltonian Monte Carlo algorithm that we used for the project. Tim will bring us through how we applied it to the quantum harmonic oscillator and the BFSS model. And then Matthew will explain how it was applied to the discrete gauge group and how we included fermionic fields. So if we start off by considering a bosonic field, it's just a scalar value function of some characterization of time and space. You can use this to describe a membrane, so this would be the value of the eighth coordinate at time t0, the point on the membrane where sigma 0. So matrix regularization is a way to swap depending on spatial parameters, because you effectively swap spatial degrees of freedom for matrix degrees of freedom. So we can go from here depending on time and space, depending on time, or x is an n by n matrix. And then if we take n towards infinity, we get the continuum Bayer graph. So gauge gravity duality. The gauge gravity duality relates the d+1 dimensional theory of quantum gravity to the gauge quantum field theory without gravity in d dimensions. So there's one less dimension due to the hologravity principle. Duality means that whatever occurs on one side of the duality can be studied through the mathematics of the other, facilitating the exploration of difficult concepts. The BFSS model describes a gauge matrix model of quantum field theory in flat spacetime with an action that can be derived by a dimensional reduction of the superrealities. It's due to 10-dimensional supergravity, and the large matrix unit is conjectured to be a description of n theory. So we're working with quantum field theory, so given an action we can write a path integral like this. And if we decide we're content with just getting observables, we're able to turn this into a partition function, and we can consider it as a statistical system. This can be done by weak rotation, where we move from time to imaginary time. And what this allows us to do is, rather than having an imaginary input, we're able to move to something that resembles more of a partition function. Now, if we have a partition function, we can start calculating observables. So say for some observable g, we'll be able to calculate the expected value like this. So in practice, it involves integrating over paths of matrices through Euclidean time, which isn't trivial for interesting systems. But through Markov chain Monte Carlo methods, we have another way. So a set of samples called a Markov chain are they're representative of the probability distribution of interest. So in our case, this is the probability distribution of your interest. The expectation value of an observable is obtained by taking the mean of the observables across the set of samples in the Markov chain. So we still need to draw samples of past Euclidean time, which is a problem obviously because with computers you can't consider continuous things. So we need a solution to that problem. The solution is to put it on a lapse. So we take the period beta of Euclidean time and split it into lambda steps, so that any path is now represented by a list of lambda sets of d, which is a number of dimensions, n matrices. This idea is that in the large lambda limit, the continuous path is recovered again. So we just started out with a bosonic field. Through matrix regularization, we stop depending on spatial and degrees of freedom, swapping for a matrix degrees of freedom. Use a Rick rotation to go from path integrals to a partition function, and then discretize it so it will be compatible with our computation methods. So moving on, the Hamiltonian Monte Carlo method is what we use to do all our computing basically. It's just a method for getting samples to the target distribution using Hamiltonian dynamics. So we begin with some initial position and take a random momentum from our target distribution, and together we call this our current state. We evolved the state using Hamilton's equation with numerical integration, so in that case we use leapfrog integration, or just some sort of symplectic integrator, and that gives us a new proposed state. So it's important to note this isn't modelling physical evolution of the system, we're just moving through the phase space to come up with another proposed state, just as a suggestion. So once we've done that, we can get the Hamiltonian of both current and proposed state, and we can use the Travis acceptance criterion to decide whether we want to keep the current state or accept the proposed one. So what we do is calculate alpha, which is just exponentiating the difference between the current Hamiltonian and the proposed Hamiltonian. You can effectively treat alpha as the probability of acceptance. So if alpha is equal to or greater than 1, we accept the proposed state. If it's less than 1, say 0.7, then there's a 70% chance that we accept it. And then if we accept the proposed state, we keep the new position. Otherwise, we keep the old position, and P is discarded. Again, P is just a tool for exploring the phase space. Right, I'll hand you over to Tim to explain how we apply this to fundamental later.
Right, so now we kind of want to put everything together into an actual algorithm of sorts. So we start off with this quantum harmonic oscillator, and we want to try and run an algorithm that performs these Hamiltonian Monte Carlo simulations. So first off, we need this Euclidean action here. This is how we just defined it here, and x is just the position with n by n Hermitian matrices. So then we need the lattice discretization of this, which I just explained. So we end up with this here as our action here. So then these are just your position matrices here, and each one is dependent on one after as well. And then we also need the Hamiltonian to simulate this Hamiltonian evolution. So we start off, we just add in this extra trace of these momentum matrices here, and then we'll use that for our Hamiltonian. So we also want to check if our results are right. So one thing we can check compared against like known observables. So one thing that's useful is the expectation value of the action. So we compare this with the analytic results, this one here, and this is what we use to calculate the expectation value of the action for our system. So these are the two plots we get. So this is here for 10,000 Hamiltonian iterations, and you can see like in the first few steps here, there's like a dramatic decrease in the forced out conversion on this analytic limit. It's called the thermalization. So basically, any samples you take in this region, they aren't distributed according to the target distribution. So as long as you run it long enough that you start converging, you pass the boundary period, then your algorithm should start oscillating above this actual value that this what we saw. So it shows that we're right. And then we ran another check against this Blakeney or semicircle distribution. It's basically the distribution that arrives from this distribution of eigenvalues of random matrices. So we can use this as a check as well. It's basically a scaled semicircle distribution. So as the dimension of the matrices increases, it should get approximately better this sort of semicircular distribution. And you can kind of see this here. This is for 5 by 5 matrices. And it's not really very circular, but then we moved up to 25 by 25 matrices. It's a much nicer distribution. So again, that's a good sign that our algorithm is correct. So we want to add this gauge freedom. So we want to explore gauge freedom in this matrix models. So due to the cyclic property of the trace, the action that we're using is invariant among this global transformation. This G here is remember the unitary group. So because this du1 cancels into joint action, it's effectively an SUN invariance. And then we can promote this variance to a local gauge symmetry by we define this thing called covariant derivative. This A here, the gauge field depends on this here's imaginary time. And when we put this imaginary time onto a lattice, this gauge field manifests itself in terms of these things called linked variables, which is the GN down here. So basically, it's how, as we move through the lattice, it's how dependence of this gauge field is like fell from like one link, one step on the lattice to the next. So then this is how we define it there. And a bit far. Yeah, there you go. Yeah. So as I said, you use these link variables to define this covariant derivative here. So these are the link variables here on the side. This is just the same position matrix we had. This A is the lattice spacing, so in between just like one point of the lattice and the next. And then we will apply this change of variables. We can apply as much as we want. And then if we choose a gauge, a certain gauge, depending on whatever we're working with, you can choose a gauge so that just one link on the lattice feels this sort of gauge field. So we call this the holomia, which means just one thing on the lattice is this gauge field. So we call this D in our, so this D here. So it's just basically a diagonal matrix. These here, these thetas, we define this as our gauge. So it's just diagonal matrix with each theta along each diagonal. So we want to sort of put all this into work with our harmonic, common harmonic oscillator. So we add in this gauge, which is called theta, and then each theta has an associated momentum with it in the same way that the x and p had the x is an associated p from the Hamiltonian Monte Carlo. So we just evolved these in the exact same way we did before, and except now we just have a gauge term. Except the only difference in this term is that we have an extra term in the action, it's called the off term, and it's just introduced to maintain the consistency of the path interval formulation once we introduce this gauge here. So pretty much now we just transition into this bosonic BFSS action. It's pretty simple theoretically to transition from this gauged quantum harmonic oscillator into this BFSS model. The only difference here is in the potential guidance here. So and then this is just a Euclidean action. Again, we do the same thing with all lattice. These here are the Colm elements again. And these xi's we sort of moved up. So now there's multiple x matrices per site on the lattice. So this I runs from that 1 to 9. This represents the 9-dimensional membrane in this space here. And apart from like computational time, there's no real problem. Just transition from the to the gauge quantum harmonic oscillator and then to the BFSS. So everything worked out pretty well. So these results we got. This result on the left here, this is already established results. This is the extent of space plot here. So this is like extremely computation heavy. So we just sort of zoomed in on this little area here where there should be a phase transition around 1 here. So this is just temperature around the bottom. So as you increase the temperature, we expect to see a phase transition going up here. And these results we only got to plot 5 here. It takes so long to run, but as you can see around 1 here, you can see a phase transition up here. This just sort of represents the size of the membranes we're working at. It changes the temperature, increases. Yeah. So this is the polyacog grid. This is another we want to try and plot. Again, this is the results here. And again, we just sort of zoom in on this sort of phase transition region here. As Jack was talking about the gauge gravity duality, this is on the gauge side of it. So if you want to see what the implications is on the gravity side, this sort of represents the deconfinement here. So after this, so along here is sort of confined. If you want, it's basically in terms of black holes, it's called a Hawking age transition, I believe. So at these low temperatures, black holes sort of weak, and as you move up this phase transition, they're more stable and bigger. So that's what we found there. And now I'll pass over to Matthew, and he'll explain these results from fermions.
Hi. Yeah. So now we've kind of got our results established for our bosonic BFSS, and we've used our continuous gauge group. I'm going to kind of back up and talk a bit more about the choice of gauge group. So the gauge is sort of brought in through this continuous gauge field, but the way it shows up in our matrix models is actually just through these link variables. And the link variables are just matrices that are in our model. So there's nothing really stopping us from choosing them to be from a discrete group as opposed to a continuous group. Doing this with the symmetric group as the discrete group was kind of investigated analytically by Denjo and Sanjay there at DIAS. And they found that a phase transition occurs at low temperature in the harmonic oscillator model. So I wanted to look a bit into that from the Monte Carlo side. So I guess the place to start is, well, how do you actually get a Monte Carlo Markov chain to look into this statistics? Well, the first thing is that the action is invariant under choices of holonomy element from conjugacy classes in SN. So that brings down the dimensionality of the problem quite a bit, because there's like n factorial elements in SN, and then there's a lot less elements or a lot less conjugacy classes than elements. So right away you can choose samples in the Monte Carlo simulation to take a partition or conjugacy class rather than a specific element each time. But still we have to kind of walk through our space of a discrete space of partitions rather than a continuous space like the matrix variables. And kind of doing that like in parallel is a little tricky. But the first thing you might think to do is just kind of randomly choose a different partition at the start of each Hamiltonian evolution. So at low n, this did work, and this is the graph that's shown up here now. So for n equal to 3, you see that the hybrid Monte Carlo results fairly closely track the analytic curve that's predicted. So this is the expectation value of energy versus beta. But we don't see any phase transition here, because n is not large enough for it to really be a good approximation of a continuum model. So as you pump up n to larger and larger numbers, this kind of random choice of partitions at the start of each Hamiltonian evolution was very ineffective. So I got a very high rejection rate, and essentially what was happening was that each time that the Hamiltonian evolution was occurring in a given partition, it was finding the maximum of the probability distribution for that partition, but that doesn't necessarily correlate to a maximum of the probability distribution for a different partition. So a new approach was needed, and kind of glossing over a lot of trial and error, the solution was to use something called mixed Hamiltonian Monte Carlo. So in the same way that in general Hamiltonian Monte Carlo, you sort of insert this momentum variable to make up for any increases in probability that might need to be made to step between minima in the overall probability distribution. Here in mixed Hamiltonian Monte Carlo, we introduce an auxiliary momentum and position for the discrete variable. So now we've got something to sort of walk around in a continuous space with that correlates somehow to the discrete variable. So we give a kinetic energy term to the auxiliary momentum, and we just take a constant potential energy in terms of position. So we evolved this auxiliary momentum and position along with the normal position and momentum of the actual matrices. And because we put our position on a circle, whenever it hits a barrier, we sort of do a check to see how much energy would be required to jump to a different partition with the same matrix values. And if the auxiliary momentum has enough kinetic energy to make the jump, then we accept that. And if it doesn't, then we get reflected. So accepting being taking the new partition, and being reflected meaning literally the auxiliary position goes back the way it came, and we don't accept the new partition. And then we do the same Metropolis Hastings check that Jack was talking about, and that ensures that overall our Markov chain does represent the probability distribution that we want to. So this process did work. Here's the plot for n equal to 10. So as you can see, the analytic results very definitely show a phase transition. The hybrid Monte Carlo results also show a phase transition. It's not perfect fitting to the analytic results, probably because of lattice defects. Like lambda was not literally taken to be infinity, and that has its effects. But for a statistical recreation of analytic results, this is not too bad. So I guess now that that's been set up for this somewhat trivial harmonic oscillator case, it's sort of exciting prospect to apply it to things that actually have a dual gravity theory and see what the effects of sort of messing with the gauge in those theories would be. So yeah, now I'm going to talk a bit about extending the BFSS to include the fermion part of the model. So sort of leaving behind the discrete gauge and going back to SUN gauge theory. If we take our fermion fields just to be fields of with Grassmann numbers at each point in space and time, we can kind of do the same procedure that Jack described, where we matrix regularize, Rick rotate to get a partition function, and then discretize things to put it on a lattice. So this time, as Tim was sort of saying with the bosonic BFSS, things become much more computationally expensive, and even more so when you add in fermions. So I looked at a 2D version of the BFSS model. So essentially, we're looking at something that has 2 supersymmetries rather than 16 in the BFSS, and there's a 2-component Majorana fermion. So choosing gamma matrices in a sort of nice way, I got this as the fermionic part of the action. So this would be added on to the action that Tim was showing earlier. So I guess just to say that there's a term in here that's sort of been inserted to make up for lattice defects, and that's the Wilson term. And it sort of covers over any problems created by fermion doubling, which is where basically the linearity of the derivative is messed up by putting things on a lattice, and you get multiple results rather than just, or multiple solutions rather than just one. And so we put in this Wilson term to get rid of those solutions, and then in the lambda goes to infinity limit, that Wilson term should really be 0, or it is 0 in the lambda equals infinity limit. So that's a nice sort of way of solving that problem. So then if we use a basis of SUN's the algebra, this action can be written in terms of a pretty big matrix, which is why the dimensionality and computationally expensive nature of the fermionic system exists. So yeah, we have this 2n squared minus 1 lambda squared matrix multiplied on each side by a vector of Grassmann numbers. And then by Grassmann integration, this contribution to the partition function is just a Pfaffian of the big matrix. And assuming that there's no sign issue, we can kind of write that as a determinant. So yeah, we're taking that to sort of as given that if there's no sign issue. Denjo again looked into that in the past. So now that we've seen that we can rewrite our Pfaffian in terms of a determinant to the power of -1/4, we can now use pseudo-fermions. So rather than having to work with Grassmann numbers, we can actually use scalar valued vectors, multiplying our massive matrix on either side, because the integration over the pseudo-fermions would give the determinant of that matrix. So now the Hamiltonian Monte Carlo basically has an additional step at the start where we sprinkle pseudo-fermions from a Gaussian distribution, and then solve for the actual psi vector. And then the bosonic side of the Hamiltonian Monte Carlo is sort of unchanged, except for that we have some additional forces due to this matrix that the bosonic fields are involved in. So here are my results for the two supercharged model. We can see that there is a low temperature and high temperature sort of region with different behavior. So here we have the extent of space on the y-axis and temperature on the x-axis. So there is sign there of a phase transition for sure. There's not the expected high temperature behavior that was seen in the bosonic only case, but these results are for n equal to 4 and lambda equal to 4. So I expect that pushing up n and lambda, we get something closer to results that represent maybe reality or analytic results. But to do that, I'd need more efficient computational techniques, which I just didn't get around to before this presentation. So again, sort of proof of concept that things are working, but yeah, not the complete results that we were hoping for there. But yeah, that sort of brings us to the end of our presentation. So thanks very much for listening. I suppose take any questions then.
Any questions?
Okay. Matthew, can you tell me what potential did you use for the scalars in that case? In your n equals 2, did you include the commutator squared? Can you hear?
Sorry, I just realized I was muted. Yeah, I did. Yeah, the same. Yeah, the same bosonic potential is used.
Okay.
Yeah.
Excellent.
Yeah.
Okay, so I'm not very familiar with this topic. So it's to do with the numerical techniques you use. From what I can tell, you're doing something on a lattice, but I didn't see the size of the lattice here. Maybe I missed what parameter refers to the number of particles.
It kind of depends on like, it's up to your choice, to be honest. Like we started off with just like 5 points, and then eventually when we moved to the BFS, we had 22 something. Yeah, 22 points on the lattice.
It was labeled lambda in that notation.
So your ideal is to have as many sites on the lattice as possible, but with the laptops we've been using, you have to keep it fairly reasonable.
Yeah. So the more sites you take, the more closely you approximate the continuous bit.
So you have some duality. So you start off in, I don't remember how many dimensions, and it's dual to a gravity theory in an extra dimension. But then you do some type of dimensional reduction to get it down to 1 dimension?
Not exactly. Well, we just started off. That was from the BFSS stuff. We started off just the quantum. You don't really take into account the duality for like the quantum oscillators.
Yeah, but so when you said there, you mentioned there's a phase transition that's dual to the Hawking-Page transition.
Yeah.
So in what theory of gravity do you have that's dual to this? Like, does this dimensional reduction affect?
I believe it's 11-dimensional supergravity that's dual to.
Yeah, but then does the dimensional reduction that you have to perform in order to actually do these calculations affect this duality or not?
No, it doesn't affect it. According to higher powers, I suppose, like Maldacena, I think put forward this particular duality. So, yeah, sort of deferring to his judgment on that.
Okay.
Just to clarify, the duality is between the quantum mechanical model itself, which they're studying, and type 2a supergravity in 10 dimensions, which lifts on a circle to 11-dimensional supergravity. And so you've got the duality to an 11-dimensional supergravity. And the description that as these guys began with was that a membrane, which is a 2-dimensional extended surface propagating in 11-dimensional supergravity, should be described by this quantum mechanics, and it's that relation that relates it to 11-dimensional supergravity.
Okay.
So that membrane is generating the gravity and the rest of it
Okay, I see.
in the 11-dimensional thing. That's roughly the conceptual idea.
Back into it.
So I have one follow-up question. So does this picture should depend somehow on the geometry of the space-time? So do you consider like flat space-time in your case, or I mean the ADS-50, for example, is working particular choices of geometry, but in some others.
The membrane begins. The matrix model is derived by beginning in flat 11-dimensional space-time, but the quantization of it and the fluctuations of it induce corrections so that it's a non-flat curved space in 11 dimensions. In 10 dimensions, the 10 and 11 dimensions are essentially the same. But one of them is just a description of the other. But the temperature is related to the black hole in that one. So it's a black hole geometry in 10-dimensional type 2A supergravity with additional charges in the background. That's the geometry. So it's quite a non-trivial geometry.
You mean it just somehow is emergent from this BFSS model?
It should be emergent from it. The conjecture is indirect. It's a conjecture. The derivation of it is the two should be the same. How to see that it's emerging from this is the challenge.
Okay, thank you.
Right, if that's all the questions, the guys were exactly on 30 minutes, including questions. So well done. And next up it's Ben.
That's one more.
Okay, so the second talk today is Benjamin Clark, and he was working on a project proposed by Venus, changing the fundamental constants of the universe.
Yeah, so my project is changing the fundamental constants of the universe. So I'm just going to quickly introduce, just give a quick introduction, then I'll go through a brief thermal history of the universe, go into sort of universes that we've then simulated, and then sort of finish off. So overall, what Venus and myself and past summer students of Venus were looking to do was develop a deeper understanding of how the fundamental constants of nature shape the evolution of the universe. And then, so the way we did that was we would create models of how the universe would evolve if the value of a given fundamental constant was different than what they are in the universe we have here. So previously, summer projects have looked at changing the speed of sound relative to the speed of light, as well as just looking at the speed of sound itself and changing that. They've also looked at changing the gravitational constant, the mass of the electron, and the relative strength of the fundamental forces. So this year, we've studied the effect of the amount of dark energy in the universe. So that ties in with the cosmological constant. So we have assumed throughout this that the dark energy density has remained constant throughout the history of the universe. Recently, DESI has published, so it's an observatory, they published findings that could suggest that that's not actually the case, that has remained constant throughout the history of the universe, but that's what we've gone with for this project. So that's, we can see here, so the blue line is the density of radiation, the orange line is the matter density, and the green line is the density of dark energy. And then I've also put in grid lines which are quite faint, you might not be able to see them, but you can see them marked at the top of various points during the history of the universe that we've looked at. And then finally, you might just notice, so early times, you can see that the density of radiation was high, so the universe was radiation dominated. Then it was matter dominated after that, which is when the galaxies, most of the galaxies were formed, and then finally today we're living in the dark energy dominated universe. So that's seen by the fact that the universe is expanding at an accelerated rate. So we're looking to change the amount of dark energy in the universe, and see how it affects certain events in the history of the universe. So computationally, we don't have enough power to look at the whole history of the universe. I don't think anyone would. So we've focused in on certain points in the history of the universe. So we've looked at the quantum chromodynamic phase transition, so QCD phase transition, neutrino decoupling, Big Bang nucleosynthesis, BBN, and cosmic microwave background, so it's CMB. You might have noticed on the previous slide, I'd also marked in the electroweak phase transition, but we didn't really look at that. So the electroweak phase transition is when the Higgs boson got an expectation value, which is when the particles got mass, got their masses. But that's a phase transition similarly to QCD phase transition, and isn't really affected. So when that happens, what temperature happens, that isn't really affected by changing the amount of dark energy in the universe. So we didn't look at that too much, that's why I've left it out there. So briefly, just to sort of talk about the various points. So at the very beginning of the universe, all fundamental particles are in thermal equilibrium, creating a type of particle soup, if you want. So thermal equilibrium just means that if a process is in thermal equilibrium, it means it has equal probability of happening in one direction as it is happening in the other. At around where the temperature is about 150 megaelectron volts, strong interactions between quarks and gluons become important, and baryons, so three quarks, protons and neutrons, and mesons, which are quark-antiquark pairs, are formed. So to create this, we're using natural units, so that basically involves converting everything into electron volts, assuming that the speed of light is equal to 1, Planck's constant equals 1, as well as other things. So that's why temperature is written in terms of electron volts, not Kelvin, as you might sort of see otherwise. Sort of after that, we come to sort of neutrino decoupling. So neutrinos are also a fundamental particle, and they interact with the particle soup through the weak interaction. So they're not affected by the QCD phase transition. So that's the weak interaction there, just a sample of it. So the weak interaction is carried by W bosons and Z bosons. W bosons are when are carry charge, whereas Z bosons are neutral. So when we're looking at certain processes, we're then interested in the interaction rate of each process. So the interaction rate, you can sort of think of it as basically being the rate of how often it happens. So that's defined as sort of capital gamma is equal to n, where n is the number density of the given particle, sigma, which is the cross section, so the probability of it happening, and then v, which is the velocity. So for very early on in the universe, everything was relativistic, so we can sort of take v is equal to 1 and then neutrinos here are also treated as relativistic, and actually because they're so light, they're actually thought not to have mass for a long time. Turns out that they do. We also treat them as relativistic, so V is equal to 1. Number density will scale approximately like T cubed, and then for weak interactions, the cross-section is approximately Fermi's constant squared, so Gx is Fermi's constant times T squared. So that means that the interaction rate is approximately Fermi's constant squared times T to the 5, so scales as T to the 5. So we're then interested when the interaction rate is equal to the Hubble parameter. So the Hubble parameter describes how quickly the universe is expanding. So when the interaction rate is approximately equal to the rate that the universe is expanding, that defines when that interaction will come out of thermal equilibrium. So previously, the interaction rate would have been greater than the Hubble parameter, and there would have been enough sort of energy present for the interaction to go both ways. After, so when it's less than the Hubble parameter, there's not enough energy, so the interaction will only go one way, and we say that that particle or that interaction will decouple. So in our universe, neutrinos decouple after approximately 1 second, and when the temperature is about 1 mega electron volt. And then, like I've said, so setting the interaction rate equal to the Hubble parameter, that will sort of define when the neutrinos decouple in simulated universes that we'll make. So the temperature and the time won't be the exact same. So next then we have the Big Bang and nucleosynthesis, BBN. So early in the universe, baryonic matter, so protons and neutrons, was mostly in the forms of actual protons and neutrons rather than combined as nuclei. And these would convert to each other via beta decay, again in thermal equilibrium. So it can go both directions. So around the same time as neutrino decoupling, the neutrons were frozen out, so it became only energetically feasible for neutrons to sort of converge down the way into protons, so the bottom interaction there. And then sort of over the next period of time, neutrons and protons would then combine to form light elements like deuterium, helium, like the processes described at the bottom. So to find the interaction rate of this, we're looking at the first set of interactions, or the first set of processes on top, and we want to find the cross-section for each of those, and using the same relation that I showed earlier, I haven't written it again, so gamma is equal to n sigma v. V is equal to 1, because again we're treating they are relativistic at this point, and so we end up with this expression here where tau of n is the neutron lifetime, Q is mass difference between a proton and a neutron, and T again is temperature. So we can set this equal to the Hubble parameter and solve for T, and that will give us when this occurs in our universe. So in the universe we live in here, this BBN sort of happened between, so the neutrons were frozen out at about 1 MeV, and then sort of towards 100,000 electron volts, we sort of see deuterium and helium forming, and that's sort of around 3 minutes. And then finally, so we have the cosmic microwave background, the CMB. So the cosmic microwave background that we see today was formed as a result of the first atoms being formed. So we have at this stage we have the nuclei, but there's no electrons. The electrons are all still free. So in recombination, these electrons are then become bound to the atoms. So photons will only interact with charged particles, and the free electrons that are now bound to or that aren't free anymore, they're now bound to the atoms. The photon just sees an atom as one single uncharged particle, so it no longer interacts. That then means that the mean free path of the photons then becomes longer and longer, and we say that the photons decoupled from matter. So this actually causes the universe to then become transparent. And so the last scattering is what we see today. So when the photons have decoupled and their wavelengths become long enough that their mean free path is longer than the horizon length. So, like I said, so before photon decoupling, photons primarily interacted with matter through interactions with electrons. So through Thomson and Compton scattering. The difference between Thomson and Compton scattering is one is for relativistic particles, one for non-relativistic particles. Again, I've just shown the process and the Feynman diagram at the bottom. And the interaction rate is given by this expression here. So where the zeta of 3 is the Riemann-Zeta function, and that's just a value. Eta is the baryon to photon ratio. Sigma t is the Thomson cross section, and the xe of t is the ratio between the number density of electrons and baryons. So we can calculate this xe from the Saha equation there, and so we can sort of see, once we solve xe as a function of t and put it into now we can sort of see where the Riemann-Zeta function and the eta come from. The BH in the exponential at the back is just the binding energy of hydrogen. So again, we set the temperature at which the photons decouple by setting it equal to the Hubble parameter. So what is the Hubble parameter? Well, it's a measure of the expansion of the universe. We can get it from the Friedmann equation here. So the Friedmann equation is found by solving the Einstein equation in the FLR metric, just a certain metric that Friedmann, along with others, came up with. So omega r is the density of radiation, omega m is the density of matter, and omega lambda is the density of dark energy. So if we evaluate it today, that means that h is equal to h0, that's just the Hubble constant, which is the Hubble parameter of what it is today. And we find A, which is the expansion parameter, which measures the sort of rate of expansion. We set that equal to 1 for today. It is fairly arbitrary, but it's the dumb thing. So that then gives us this relation here. So 1 is equal to each of the densities today, and actually the sum of the densities add up to 1 throughout the history of the universe, but the actual densities themselves will change over time. It's also worth noting that we've assumed a flat universe here, so we think that our universe is approximately flat, and that does, so if for a non-flat universe, that does add an extra term into the Friedmann equation. So we want to maintain the second relation, 1 is equal to the 3 terms. So that means that anything added to the dark matter density has to be taken away from the radiation density and matter density, which will limit the amount that we can change dark energy density. We also want to keep each term positive. So the first way that we've changed the dark energy is we've split the change equally over the matter density and the radiation density. So, okay, it's quite hard to see, but we can see here, so this is the universe that we're in, so the change here is 0, so no change, this is our universe. And here we've reduced the amount of dark energy by 0.6, so approximately the dark energy, the amount of dark energy density of the universe today is about 0.7. So we've chosen 0.6, because shows a decent chunk without turning into a negative value or getting rid of it completely. So we can see here that the CMB, the cosmic microwave background, is just here, and that's actually in the radiation dominated part of the universe, rather than in our universe it happens in the matter dominated part of the universe. We don't think that that would actually stop the CMB from happening, and then we also have that it's very hard to see that the matter and so in our universe we're living in a dark energy dominated universe. In this simulated universe, we today would only be in a matter dominated universe instead of dark energy dominated universe. Another way that we've changed dark energy is just by basically moving out all of the density that was taken from the dark energy density, and we just moved it all to the matter density. So you can see that in this case, the universe becomes matter dominated much earlier, and we again are still will be in a matter dominated universe rather than a dark energy dominated universe. And well, in this case, the CMB would still be in a matter dominated universe. The points or the times when the CMB happens, the Big Bang nucleosynthesis and the neutrino decoupling, they do change. It's not the same. It does look the same because this is a logarithmic plot. It does change, but it doesn't change enough orders of magnitude that would show up clearly on these plots. Similarly, we've kept the matter density unchanged, so we've basically taken the change and we have we've taken the amount that we've taken out of dark energy, put it into the radiation. In this case, we'd be living in a radiation dominated universe. And then finally, we've also sort of kept a sort of proportion. So we would take 0.6 out of the dark energy, we split it between the matter density and the radiation density proportionally. So the radiation density today is to the order of about 10 to the minus 5, so it's much smaller than the matter density, and we've maintained that in this case. And we can see again that, for example, we would be currently living in a matter-dominated universe. So the universe that we live in today would look completely different because we wouldn't, for example, the rate that the universe is expanding would be much less. So you would imagine that, for example, at night the sky would be brighter because the universe itself will be smaller because it hadn't had a chance to expand as much, and also because the stars aren't accelerating away from us as quickly, sort of in the further reaches of the universe. The light would actually travel to us quicker, or travel to us would actually reach us, wouldn't travel to us quicker. So what's next? So Venus has a website with all the sort of past students. They've all contributed to their projects, and so this is sort of bringing together in one big project that we want to sort of create a model of the universe where we can change various parameters as we want and see what the universe would look like then. So there is a website for that, and we're looking to sort of keep developing that. Like to produce more simulated universes with different types of dark energies. For example, dark energy that's not constant over time, as was shown could well be the case in by defined by Daly, and Yasmin is also working on a model that isn't constant over time. And then it would also be very interesting to study how the amount of dark energy present would affect evolution of non-flat universes. So right now, the universe is approximately flat, but we don't know that was this always the case, or will it always still be the case? So thank you for listening.
Have you got any predictions?
Predictions for, like, for,
Predictions?
sorry?
Have you got any predictions? For experimental results or anything?
You mean whether these universes would be viable, or how would you see this universe if it existed?
Take it either way. Yeah, I take it.
Well, like,
So,
well,
go to the simulated universes we thought, and I think,
Yeah.
discussed it, that they all would be viable. Some of them would be too young for structure to form, or galaxies to form, but it seems BBM is viable in all of them, CMB is viable in all of them. But, for example, you see the dashed red line is the point today. For example, in the universe that you mentioned, that is matter dominated, not dark energy dominated, it wouldn't be expanding at an accelerated rate, so that would be a prediction of that universe compared to the one.
I suppose you could have some benchmarks and say, well, if we were in a radiation-dominated universe, there wouldn't be any, galaxies, for example, so then we wouldn't exist. So you could maybe have some idea of the range over which you can vary your parameter, where, potentially we could still be looking at the universe at all.
yeah, I mean, in this simulated universe here, we would be living in a radiation-dominated universe, but we can still see that, so it would be much less time that the universe would have been matter-dominated compared to our universe here, where the universe is matter-dominated for longer. So there would have been a lot less time for galaxies to form, stars to form. So probably we wouldn't be here, but there is a chance that there would be some type of galaxy, some sort of, could be planet with some sort of life, and in all of them, because we've assumed that dark energy is constant and the density of radiation and matter, they're both always decreasing in all the models, we will always end up with dark energy dominated universe. It's just a case of at what point in time this happens.
What you asked about what is the limit that you change things, you see that our epsilon is always 0.6 is because that is the amount of dark energy we have today, and if we increase it, then you have a negative abundance, which is not really meaningful.
I was wondering how you said today already, so that makes sense, yeah.
Do you know sort of what era, what the planet's constrained on how much dark energy? Do you know sort of what redshift or what era might put the planet's constraint on how much dark energy?
On how much dark energy? Well, we've just sort of set ourselves how much dark energy we haven't sort of checked and sort of found the and found how that affects the other two eras. So,
we change the amount of dark energy today.
Yeah, so we've.
Right, but that has an effect going back as well. Like when you say like CMB is viable, what do you mean by that?
Well,
Go ahead.
CMB, when we say it's viable, we just mean that recombination happens happens because the temperature reaches or cools, the universe cools down enough that the electrons will then form atoms with the nuclei, and we think that will still happen even if it's within a radiation-dominated universe. It doesn't need to be in the matter-dominated universe like it is for the universe we have now. That's all I mean by CMB is viable.
Just, you've treated matter as both dark matter and ordinary matter together. Would it have mattered if you had treated them separately?
I don't
think
think
so. Which way you treat the dark energy into dark matter or ordinary matter?
We haven't looked at it. I'd imagine for the purposes of this, not, because we're just looking at what points the various processes would happen, or like
they obey different equations of state. So
Yeah.
how did the equation of state play a role in your analysis?
So the equation of state would have come into calculating the interaction rate, and then when we're setting that equal to the Hubble parameter, to find the temperature, so we'd solve that for the temperature and then use the temperature to define when it occurs. So you can relate the temperature to the expansion parameter, quite straightforward.
But the assumption is that dark matter is evolved the same way as ordinary matter, as you see in the equation state, or you see how does omega m change?
I understand that he has that's the assumption in this. I was asking
Yeah, it would make a difference or not.
if it would make a difference.
Could I ask a very simple question that might even have a simple answer? I was very surprised to see zeta 3 popping up as if out of nowhere. I mean, is there a simple explanation for why that Riemann zeta function comes into this?
I'm not.
So we do that. It's all statistical mechanics and thermodynamics.
That's the simple answer.
Yes.
Thank you. I'm as wise as before. Thank you.
But can you get different values of zeta when you change the dark matter or dark energy constant, or is always zeta?
Not when you change the dark energy. So I didn't look in too deeply in the sort of derivation of the Saha equation, but but it does seem sort of traceable that the zeta 3 is the one that sort of keeps coming up rather than any of the other ones. So I'd imagine not.
So you see zeta 3 is on the side of big gamma, the interaction rate, it's not on the side of the Hubble. The equation at the very bottom. Changing dark energy will change the right-hand side, the Hubble rate. Whatever is on the left-hand side, the decay rate is from this particle physics.
It presumably comes from assuming that all of the particles are masses.
So this is
Because
the
then you get a sum over mass of R frequencies,
Yeah.
which is 1 over n cubed,
Yeah.
1 over n squared, and that's going to give you your
Yeah.
your zeta 3.
Yeah.
Maybe one more. But with these alternative universes kind of exercises, it's always interesting to try and figure out if there's some universes with other simple properties. Like for example, if you change this parameter, can you get a universe where the ambient temperature is, instead of 3 Kelvin, it's like 300 Kelvin, or can you get a universe where you have more helium and hydrogen, or that sort of thing?
You would, yeah. So when you change the universe, you can't see it too well because it's a logarithmic plot, but the CMB will change sort of at what temperature it happens, so that would change the sort of ambient temperature of the universe, but it wouldn't change. It just in these simulations, it didn't change sort of enough orders of magnitude. So it might go from say a couple of Kelvin, it's about 2.7 Kelvin, I think, off the top of my head. It might go up to sort of 5 or 10 Kelvin, but probably not 200 Kelvin. Of course, like for some of these, so are you asking for today?
Well,
So,
today would be
yeah.
the most interesting.
Well, there would be, I suppose there would be there might be versions where you'd manage to get to a universe where it would be just before the CMB, so in that case, there wouldn't be a sort of constant ambient temperature, it'd be the temperature of the universe at that point and still changing. But yeah, so for anything where we're sort of after the CMB, it would be the CMB temperature, which changes slightly, but not not huge events.
Okay, thanks Ben again. Last talk is Colm, James, and Adam.
Yeah, I mean, I just want from experience, Rich,
Am I right to write on the back there?
Yep.
Oh, that's a good question.
I'm not sure if the camera is working. I think it was on. I think the video is on.
The camera isn't pointing towards us.
It's just not sure. Oh, it's not pointing towards you?
Yeah, no, I think it's.
It's gone off.
so they're gonna use the black.
Oh, I see it.
Yeah.
Then you can turn it on. This is not. This one's this. Okay.
I've got this. They're trying on the camera there, so.
Are you also recording the meetings?
Yes.
I'll get the top up there.
Can you see the camera?
I'm not sure how to get the view of the.
Usually it needs to be very descriptive, doesn't mind.
Yeah.
Right. Know which board is in the frame and use that.
That's it.
If you want to control it, 1, 2, 3.
I have the.
Oh, I see.
Okay. I can keep it main to this one, if that's just the one
Just take it
frame.
down. Just put it down again for 1 second and see what is viewing. I think it's showing all 3 at the moment. So it should be okay.
That one,
Yeah, it's also that one.
We can.
It's maybe in the middle.
Yeah, can you move?
Okay.
that's pretty great. Okay.
Okay, so the last talk of today is Adam, Colm, and James. They were doing a project on causal set theory with Yasaman. So,
Thank you. Right, yes, so our project was looking at a algorithmic model of ever-present lambda, which is a model of the expansion of the universe that emits a fluctuating value for the cosmological constant lambda. So I'm going to take a look at the background theory, then Adam will look at the methods and stuff that we used, and then finally change and talk about the results. So the first thing I want to talk about is what causal set theory is, because this is fundamental to ever-present lambda and just everything we're doing in general. So first thing to note is that it's a method of quantizing space-time into discrete space-time events. So each causal set is a partially ordered set with the relation that x would be related to y if x is in the path lag cone of y. So we obey these 3 properties where if x is related to y and y is related to z, then x is related to z. This just represents the path light cone of y being a subset of the path light cone of Z. So that's our transitivity. Second is just anti-symmetry, that if X is related to Y, then Y cannot be related to X, rather. So just if one thing is in the past of another, then that thing cannot be in the past of the original thing. And then lastly, we have like a local finiteness, that if X is related to Y or past of Y, then there's just a finite set of space-time points A, such that if X is related to Y, or sorry, that X is related to A, which is like in between X and Y. So X will be related to a finite set A, which is then related to a finite set Y. So these two properties alone are not enough for us to simulate a differential manifold, which Lorentzian spacetime is. So in order to do that, we do what's called sprinkling. And what sprinkling is just the placement of these discrete spacetime points over a Poisson distribution. So the probability of finding n particles in a region of spacetime in that volume is given by 1 over n factorial times e to the power of rho sub cs v multiplied by rho sub cs v to the power of n, where rho sub cs is just equal to the average or the mean of n over v. And with this we get a differential manifold with Lorentzian symmetry, or local Lorentzian symmetry. Next thing that I'm going to write up is just a result from unimodular gravity with this, which is an uncertainty relation that delta lambda delta v over 8 pi g is greater than h bar over 2. This coupled with the density here gives us sort of the most critical relation for ever-present lambda, which is that we keep lambda proportional to 1 over the square root of the volume of the universe at any given point in time. Right, okay, next thing is that we're working in the FLRW metric for trigonometric products and order. It's given by ds squared to scale factor of the inverse a at time tau to be squared, multiplied by minus d tau squared plus dr squared r squared times theta squared plus theta d squared, not squared there. And because we're using the FLRW metric, we can use the Friedmann equations to describe the expansion of the inverse. Specifically, the first one says that h squared, which is the rate of expansion, or the rate of change of A divided by A squared, is given by 8 pi g times the mass density plus the radiation density, then plus our lambda here, and those are all over 3. And that is, I believe, all I want to say before moving on to model 1. So what model 1 is it is a algorithmic model of ever-present lambda, and there is a model 2. We're not looking at model 2. So I'm going to write up, I'm going to talk about the steps involved in it, and then I'm going to hand over to Adam to talk about what changes we made to it. Yeah, step 1 is we just increment A to another time step. What we're doing is we're taking the scale factor A to be a unit of time, essentially, where we started off at 0 for the universe being in volume 0, and then we normalize it such that A is equal to 1 at current day, and we split it up into a bunch of steps. And that's all this is. I'm going to say and step 2 is we then want to find d tau over dA, which we give by it's 1 over just a times a dot, that's equal to 1 over a to the 4 times h squared, and then that Freeman equation gets plugged in here. Step 3 is then to calculate the volumes. So first thing is that we take the volume element from the FLR double metric, which is given as dV is equal to, where is it? Oh, I'm terribly sorry. Yes, a to the 4 sine theta, and then it's dr d theta d phi. We integrate that to give v is equal to 4 pi over 3 times the integral between some initial time tau I and tau a of tau prime power of 4 multiplied by tau I by 3 times tau prime. Okay, so that this right here. Step 3 is then to take vi to do the sum from 0 to 3 of some constant c times or cj by term tau of a at time step I to the power of j multiplied by this volume part here, which is given by this incremental at each time step by this integral. That times 3 minus j d tau over dA over 4 dA. And we also write or increment tau at this step as well. So tau at the time point A is incremented by just the integral of the derivative of tau, which we have already computed from step 1. And then the last thing that we're going to do is we have a random string, or a string of random numbers rather. I'll talk about it in a sec. Just first of all, we're going to write off the means and the action. This is just an associated action with the lambda. And we just increment it by alpha times the square root of delta volume. I'll explain what alpha is in a second. Times ci, which is just a random number that is on a normal distribution between 0 and standard deviation 1. So g. Alpha here is given by the Planck length over the discreteness length of our causal set, CS, sorry, multiplied by half. And the last thing we do is we then update what lambda is. So lambda I is given by 8 pi g times the action at that time step over the volume time step. I'm going to hand it over to Adam now to talk about what we did to this.
And so then what we'd like to know is how this, what were the results of this model before we made any changes to it? So this is the Hubble parameter here, and this is the frequency of how many runs we had. So these were the results for it. And this band here is the value of Hubble parameter today that we accept it to be. So it's between 67 and 72. So ideally, you'd want this graph here just to be shifted up to the right, so the peak would be contained in that. And this is seen at small alpha and a bit bigger alpha, and then the biggest alpha here is going to be 0.012. So as you increase alpha, what happens is that your standard deviation increases. So for a small alpha, you don't find any of the ones end up being in this space here. And there's about 9,900 rules here. So you do 9,900 and none of them end up with the Hubble parameter I have today. For alpha equals 0.01, you get a few. And then as you go further and further, you do get there's a higher proportion of ones that end up in this 67 to 72 range. And now the problem is with when you make alpha bigger, you basically end up getting more crash runs. And crash runs happen when you get your Friedman equation, basically the right hand side of that becomes negative. I'll go a bit more into detail about what crash run actually means, but it just means whenever it encounters that this becomes negative, you start getting complex values for h. And so that's what we mean here. So there was 10,000 runs and only about 4 completed. So it isn't really viable to do any more higher alphas. And now an upper bound for alpha is around 0.5. So for this equation here, we expect your LCS to be roughly the Planck length, but it could be a little bit bigger. So a half is roughly an upper bound for alpha. So ideally you want to be able to test for much higher alpha if you could. And then this graph here is just basically the percentage of dark energy in today's universe, which it has a mean of 0 for all alphas, and that's around 0.7 today. So we want to increase that to around 0.7 if we could. So that's all the results that we had beforehand. And then these are things that we like to improve. So obviously we want to just increase the amount of runs that finish with a H value that we think the value is today, just to be able to look at those runs and see if they have anything in common, stuff like that. And we also want to increase the proportion of dark matter density to around 70%. We know that it's roughly 70% today, so obviously that should be something that will come up with a lot. Also, we want to increase the number of runs for a given alpha, and basically that means that we can then test higher alphas. So before you'd stop at alpha being 0.012, because you don't have enough runs to complete it, so it's not very efficient. So ideally, you could increase the number of successful runs or completed runs, then you'd be able to experiment with higher values of alpha. And then just to get a bit more insight into the crash runs, is there like a condition that all crash runs have? Do they look different from complete runs? Is there something similar on the two? That's what I'm thinking. So a crash run is whenever the H becomes negative. And this basically stems from your lambda becoming too negative. So this thing here, that's always positive, and it's always decreasing as A gets bigger. So it's just sometimes your lambda can become too negative, and that's when the whole right-hand side of the equation becomes negative, and that's when you end up with a crash run. And basically, the reason that your lambda becomes too negative is because your action becomes too negative, because the way you're dealing with there. So that's how you're dealing with your lambda. So lambda is just some constant multiplied by the action divided by the volume. So if your action becomes too negative, then your lambda becomes too negative, which in turn basically makes this whole side of the right-hand side equation become negative. And that's why more runs crash the higher alpha gets, because as you increase alpha, you basically increase the variation or the fluctuations in your action, and therefore it has a higher chance of becoming too negative. And so this is the pink line here. That's basically the criteria for when a run crashes. So if you go back to your Friedman equation and basically solve it for equal to 0. So this region up here, you can think of it as the H squared being positive region. This line would then be the H squared equal to 0 region, and then anything below that signifies that your H squared goes less than 0 and your run crashes. So ideally, whenever this your blue line, which is your actual data, whenever that touches the pink line, it crashes, which is exactly what happens here. And it happens here as well. And this happens for the majority of runs. It is dictated by this criteria. And yeah, so it just so it fluctuates, and then it hit a point, and then just goes straight down towards the pink line, and that's when it crashes. And then it looks very similar to a completed run. So that's a completed run. So a completed run, it just never goes below the pink line. Now it does get close at points, but it just never actually hits it. So your action can go as close to it as it wants, but it just can't go below it. So the first part of the graph looks very similar to the crash runs. There isn't too much difference between the start of the crash runs and the start of the successful runs. The only difference is that in your crash runs, you eventually hit a point where your fluctuations are quite big, because again, as you go along, your universe keeps expanding at a greater rate the whole time. So as you go on, your delta V gets bigger and bigger, and therefore your fluctuations start to get bigger, and that's why they're quite small here, because your delta V is small. But as you go along, you do start to get bigger variations, and then that's when these will crash. If you do get a lot of like negative numbers in a row, that force your action down, and therefore your action gets too negative. And so now there are just things that we'd like to change. So we want to be able to make more runs look like this. There's more runs just to be successful. So if we want fewer runs to crash, or in this case, to hit the pink line, then one of the things we'd like to do is to give some sort of positive bias to the action to help it up, just to force it to stay above this line. And so, if you do that, also we know that the action that we're dealing with, that should be positive for today's value. And therefore, that's another reason that as to why you'd want to give some sort of positive action, positive bias to the action. Because before, in the model, starting off, it doesn't have any preference for being positive or negative. It'd be positive 50% of the time and negative 50% of the time. But because we know it's positive, you want a lot more runs. Because it is random, so no matter what you do, some will end up being negative. But you would want as many as you could being positive. And so there's 3 different ways that we tried of doing that. So one method is just you exclude some data points when picking your list of random numbers. So you can just do something like taking a lower bound, just saying that when you're doing it, that you're only going to include ones that are maybe bigger than minus 2.5, something like that. So they're normally distributed with a mean of 0 and a standard deviation of 1. So all you're going to do is you're only cutting out a small bit of the data. You're not taking out tons, you're not taking out 50 or 60% of it. If you just get rid of maybe 1 or 2%, can that have a profound impact then on how the final answers come for H? And it turns out they do. And then for the second method is what you're doing is that these are just runs. These are all successful runs. Now what you're looking at is that you do your string of random numbers. There's 10,000 of them. And before you kind of look at anything, you just calculate the mean of them. And then what H value you get. And what you can observe is that as the mean of your cassis, your string of cassis get higher, there's a higher chance of you ending up in the between 67 and 72 for H naught. So basically what happens is that when a run does give a good H value, typically the average of your string of cassis is positive. And therefore, but at the same time, if you do go too high, then you do start to overshoot H by an awful lot. So there's some region here for a specified alpha that will end up giving good H naughts. And then the final method 3, and you just go backwards in time. So what you do is that you look at a good run, you see what ending conditions they have, what final conditions they have, and then you just make the simulation run backwards in time, but just starting from those good conditions, and then just seeing can you get it to go back to your initial conditions of today. So you start off with a H naught of 70, you see what your volume would be for a typical good run, you plug that in, and then you just work backwards and see if that makes any difference. And then that's the third method. So I'll hand you over to James then for the results.
Okay, so the first thing we're going to look at is putting a limit on the mean of the random string of numbers. So for the different alphas, you put different limits on the mean of the random numbers. Because for the higher alphas, you need to put less of a positive bias, because the higher alpha is, if you saw from the previous results, the more likely it is that the H naught will end up being an accurate value. So we put these limits on the mean, and then this is what the data looks like. Ideally, you'd want to have a few more runs. You can see here, it's missing a few there, and that's because it just takes so long to run all the simulations, especially for, this is for alpha of 0.02, which there's just so many cross runs in that it just takes ages to run. But overall, with these limits on the mean C's, you can't see there, but they're around 70. Mean H naughts are around 70, and they also correspond to good values of omega lambda of around 0.7. These are the results for removing extreme values of C of the random numbers. Top one 0.05, and you're removing around 2.7% of the random numbers and replacing them with other ones. And then similarly for the other values of alpha 0.01 and 0.012, as you go on, you have to remove less random numbers because you don't need to put as much of a positive bias on the distribution. Similarly, same as how we saw for higher alpha, you don't need to put, you don't need to turn this quite so high for higher alpha. This is 0.02. So it's the same kind of deal there. And we tried varying the initial action. This isn't too important. This is just showing that if you vary the initial action just slightly, it doesn't affect the distributions too much. Again, these would be nicer shapes if we did more runs, but it takes too long to do them all. So for finding completed runs, if you change the initial action, this is the initial action, and this is the frequency of completed runs. You can see an initial action of negative 0.05 gives around 80% completed runs for the 0.01 for alpha, and similarly for 0.02, negative 0.05 works by 2. These graphs aren't completely symmetrical, because on the left-hand side, the more negative of a bias you put on the initial action, you run into numerical errors as opposed to h squared less than 0 errors, which is what you get on the right side. So that's why they're not the exact same. Now this is plotting the scale factor against h squared. Still varying the initial action, but by a good bit more than just slightly. And you can see here that these are the larger values these are all positive S initial actions. And you can see that they stay too high because you're giving it too much of a positive bias. So h squared is staying way too high and it's giving results that aren't very good. And then you can see this S initial of 0.01 crashes, whereas if you do negative 0.01, it doesn't crash. And we think that's because going positive with the initial action, you're giving too much of a positive bias. And then for running the simulation backwards, you can see it didn't quite work. The volume, for some reason, is just decreasing way too fast. And these top graphs are scale factor versus volume. Log plot for this one, and not this one. This is with fluctuating lambda. And this is with constant lambda. And you can see that it's working perfectly for a constant lambda, constant cosmological constant. But whenever you try to implement the fluctuating cosmological constant, it stops working. This is what a good action resulting in a good Hubble parameter today looks like, compared to the actions plotted for backwards in time. You can see they all crash at around the same point. And when they're crashing, they're not crashing with h squared less than 0. They're not really crashing, they're just ending at volumes equal to 0. Because you can't go too far past that, obviously. So our conclusion, for further study, we've now found a way of getting universes which give more realistic results for the Hubble parameter and the dark energy density. And so you can start looking into how those vary with the universes that don't give a good Hubble parameter. Another thing you can try in the algorithm is that the majority of the crash runs happen very early. So if you can skip the initial few steps, that would help in just avoiding some crash runs. Another thing, you could try implementing a Brownian bridge. We tried this a little bit, which is just a random walk that would replace the string of random numbers with, it's a random walk that's conditioned to start at a specified starting place and end at a specified ending place. So you could condition it to end at a modern day value of the Hubble parameter. And you can also try to get the backwards simulation working a bit better, narrow it down a bit as to what's going wrong. So in conclusion, we've achieved our goals of strategically finding realistic universes. We've also found ways of increasing the frequency of completed runs, and we didn't quite get the backwards in time working, but we have made progress there as well. That's all. Thank you.
Any questions?
Was there something each of you found that surprised you?
How difficult the back in time was. Yeah, that was painful.
Spent quite a while on that and still don't really know why it doesn't work. By the sort of stochastic nature of the calculations for the action, it's doing something. I don't quite know what. But even from like what's plotted on those graphs there were 1,000 simulations, none of them got past A being about 0.35. And we're just not quite sure why.
Can I ask, with regard to the theory?
Yeah.
Your equation for H, for A dot here.
Yeah.
Did you try solving that directly for the continuum A?
Sorry, solving directly for what?
It's a nice integral differential equation. And I'm just wondering if somebody has tried to solve that analytically or numerically. Just to know what, if I don't put in the stochastic evolution here, what the solution is. Or maybe that was, maybe you presented it and I didn't.
No, yes, so that isn't, I think I'm right in saying that just is, it's not part of like specifically what Model 1 aims to do.
I understand, but this one, well, it looks like a reasonable suggestion.
It's solvable for lambda being constant.
No, but I wanted to put in lambda. You told me lambda. Lambda is this square root of the volume. The volume is this integral, so I put in that integral. Now I have an integral differential equation, which I can of course solve.
Yeah, no, I don't think it was something we thought to do anyway. It just that it didn't come up on the like workflow.
Presumably somebody has solved that. Sorry?
What's the question again?
Just the equation for A dot over A, with lambda being one of the square roots of the volume.
Yeah.
The volume is an integral.
Yeah.
So, well, no, it is in here. So you plug this in up here for your h squared there. So it does like play into.
But it's an integral differential equation.
Yeah.
Isn't doing it analytically.
Analytically, yeah.
Yeah.
I'm just wondering what if the solution is known to that or what it looks like.
Constant lambda, lambda which is
well, lambda is not constant.
Yes.
It is the square root of it's the square root of the integral up to tau of this integral here.
Yeah. I know there is issues with like Einstein's equations not permitting a fluctuating lambda. So that there's a reason why we couldn't use Friedman's other equation that relates to like the second derivative of A to A. I'm not sure if that has issues with just solving this analytically and using that as a model.
I appreciate it wouldn't be self-consistent with regard to that, but you did mention the volume. What's the word that goes with that? When you put in the fixed volume.
You can write it all in the equation.
And we did look at this a little bit for like 10 minutes, and then I was like, oh, it's kind of hard.
Yeah, so lambda is secretly a function of volume, which is complicated.
It's an integral.
Yeah, formally it's an integral, doing the integral.
I mean, analytically it can be difficult, but you can do it numerically.
Yeah, that's what they do. They numerically integrate.
But numerically, but then put in the stochasticity as well.
Yes.
What does it look like when you, essentially what I'm asking is what happens when you don't put in the stochastic thing? What does the evolution look like?
But what do you mean by non-stochastic?
Well, it's
Is it still time?
It's a straightforward integral differential equation.
Yeah, but do you mean constant or some particular deterministic dynamic?
I mean the solution to the equation.
Right, but what are you substituting for lambda?
Square root of the integral for A. The appropriate volume, which is determined by A.
Is this numerically or analytically?
You will have to do it numerically. I mean, there are techniques for solving integral differential equations, which I'd be surprised if it worked exactly, but you can solve integral differential equations.
Somebody's looked at this already.
I assume so, that's why I was asking.
It's such a simple thing. For constant lambda, there are solutions, but
No, but it's not constant.
Is that now lambda is an integral? Yeah.
It's second.
Yeah.
It's around the second value analytically, but it's not if you do it numerically.
They can do it numerically. I think they can. Yes.
If you didn't do it, that's fine.
Oh yeah, no, it wasn't something that we looked at.
Maybe a project for next year then.
Could you explain what's happening a bit more physically in step 3 and 4? I wasn't really able to follow that.
Step 3 is just the calculations of the volume. So the volume is given by like these 4 different parts of the volume. So there's some constant here. I think they're like, it's either like -1, 1, 3, or -3. I don't know what the order of those numbers are, but they are the correct numbers. Then it's multiplied, like this is multiplied by these like 4 volume parts at each time, which is just given as a function of like the derivative of tau and tau, and then that integral. Step 4 is we take an action that's associated with lambda and we increment it by some random step. The idea being you run enough of them and then it hopefully spits out like a bunch of answers. You can filter out the ones that are physical, you keep the ones that are physical by checking like the known value for H0, and then update lambda by that. Is that what you're asking?
Well, why would the evolution be like kind of stochastic on a normal distribution?
That's just sort of I can't remember how the mean and standard deviation were like come up with. I know the mean being 0 is just like in for an equal chance for it to be positive and negative. Something about the central limit theorem in there that I can't figure out. I'm sure guys can explain more about that if you want. Then like this is just sort of the calculated volume from this here. Like you just come from the volume element of the metric.
Okay. That's good. Yeah, I understand what you're doing. Thanks.
Okay, if there's no more questions, maybe let's thank all the speakers. Thanks everyone for coming, and there's two more afternoon at 2:30.
Is it the same Zoom link?
Yeah, that's true.
No, but I
wrote that equation on the board and I was like,
See, the video may well come from like